Website security principles have had a thorough overhaul over the past few years. This is primarily due to the ease of access to malicious tools, starting from DDoS attacks to remote code execution. A full-fledged web application security platform will need to check the major culprits like cross-site scripting, one of the riskiest attacks to perform with similar level of rewards when conducted properly. While the attacks from the client side on most occasions, they can be configured to work remotely against most secured platforms as well. Let us go through some of the topics to be covered in today's video on cross-site scripting. We start by learning the basics of cross-site scripting and the formative arguments that go into play when conducting this attack. Next, we take a look at ways a cross-site scripting attack starts and how the hacker leverages vulnerable web applications and systems to infect users and servers alike. Moving on, we read about the three distinct categories of attacks when it comes to cross-site scripting. We then go through some of the industry recommended measures to prevent systems from falling prey to cross-site scripting attacks. And finally, we complete a set of cross-scripting challenges, highlighting the ways hackers think and how a simple line of code can open up vulnerabilities if not configured correctly. Let's start by learning about cross-site scripting from a layman's perspective. Cross-site scripting, also known as XSS, is a type of code injection attack that occurs on the client side. The attacker intends to run harmful scripts in the victim's web browser by embedding malicious code in a genuine web page or online application. The real attack takes place when the victim hits the malicious code-infected web page or online application. The web page or application serves as a vehicle for the malicious script to be sent to the user's browser. Forums, message boards, and online pages that enable comments are vulnerable vehicles that are frequently utilized for cross-scripting assaults. A web page or web application is vulnerable to XSS if the output it creates contains unsanitized user input. The victim's browser must then parse this user input. In VBScript, ActiveX, Flash, and even CSS, cross-site scripting attacks are conceivable. They are nevertheless most ubiquitous in JavaScript, owing to the fact that JavaScript is most important to most browser experiences nowadays. The main purpose of this attack is to steal the other user's identity, be it via cookies, session tokens, and other information. In most of the cases, this attack is being used to steal the other person's cookies. As we know, cookies help us to log in automatically. Therefore, with the stolen cookies, we can log in with other identities. And this is one of the reasons why this attack is considered as one of the riskiest attacks. It can be performed with different client-side programming languages as well. Cross-site scripting is often compared with similar client-side attacks, as client-side languages are mostly being used during this. However, an XSS attack is considered riskier because of its ability to damage even less vulnerable technologies. Most often, this attack is performed with JavaScript and HTML. JavaScript is a programming language that runs on web pages inside your browser. The client-side code adds functionality and interactivity to the web page and is used extensively on all major applications and CMS platforms. Unlike server-side languages such as PHP, JavaScript code runs inside your browser and cannot impact the website for other visitors. It is sandboxed to your own navigator and can only perform actions within your own browser window. While JavaScript is client-side and does not run on the server, it can be used to interact with the server by performing background requests. Attackers can then use these background requests to add unwanted spam content to a web page without refreshing it. They can then gather analytics about the client's browser or perform actions asynchronously. The manner of attack can range in a variety of ways. It can be a single link which the user must click on to initiate a JavaScript piece of code. It can be used to show any piece of images that can be later used as a front-end for malicious code being installed as malware. With the majority of internet users unaware of how metadata works or the ways in which web requests are called, the chances of victims clicking on a redirecting links is far too high. Cross-site scripting can occur on the malicious script executed at the client side using a fake page or even a form that is displayed to the user. On websites with displayed advertisements, malicious emails can also be sent to the victim. These attacks occur when the malicious user finds the vulnerable parts of the website and sends it as appropriate malicious input. Now that we understand the basics of cross-site scripting, let us learn more about how this kind of attack works. In the first place, we have the website or the web browser, which is used to show content to the victim, or which is the user in our case. Whenever the user wants to grab some content from the website asks the data from the server. The server provides this information to the website and the web browser, which ultimately reaches the victim. How the hacker comes into play here: it passes on certain arguments to the web browser, which can be then forwarded back to the server or to the user at hand. The entire cross-site scripting attack vector means sending and injecting malicious code or script. This attack can be performed in different ways. Depending on the type of attack, the malicious script may be reflected on the victim's browser or stored in the database and executed every time when the user calls the appropriate function. The main reason for this attack is inappropriate users' input validation, where the malicious input can get into the output. A malicious user can enter a script which will be injected onto the website's code. Then the browser is not able to know if the executed code is malicious or not. Therefore, this malicious script is being executed on the victim's browser or any faked form if that is being displayed for the users. There are many ways to trigger an XSS attack. For example, the execution could be triggered automatically when the page loads or when a user hovers over specific elements of the page like hyperlinks. Potential consequences of cross-site scripting attacks include capturing keystrokes of a user, redirecting a user to malicious websites, running web browser-based exploits, obtaining cookie information of a user who is logged into a website, and many more. In some cases, cross-site scripting attack leads to complete compromise of the victim's account. Attackers can trick users into entering credentials on a fake form, which can then provide all information to the attacker. With the basic working of a cross-site scripting attack out of the way, let us go over the different ways hackers can leverage vulnerable web applications to gather information and eventually breach those systems. The prime purpose of performing XSS attack is to steal the other person's identity. As mentioned, it may be cookies, session tokens, etc. XSS may also be used to display fake pages or forms for the victim. However, this can be performed in several ways. We have a reflected attack. This attack occurs when a malicious script is not being saved on the web server but is reflected in the website results. Reflected XSS code is not being saved permanently. In this case, the malicious code is being reflected in any website result. The attack code can be included in the faked URL or in the HTTP parameters. It can affect the victim in different ways, by displaying fake malicious page or by sending a malicious email. In a reflected cross-site scripting example, the input of a search form is reflected on the page to show what the search key was. An attacker may craft a URL that contains malicious code and then spread the same URL via email or social media. A user who clicks on this link opens the valid web application, which then runs the malicious code in the browser. This script is not stored in the web application and malicious code is shown only to one user. The user that opens the link executes the script, and the attack is not necessarily visible on the server side or to the app owner itself. The next variant is the stored cross-site scripting attacks. This occurs when a malicious script is being saved on the web server permanently. This can be considered a riskier attack since it has leverage for more damage. In this type of attack, the malicious code or script is being saved on the server, for example in the database of the website. It is executed every time the users call the appropriate functionality. This way, stored XSS attack can affect many users. Also, as the script is being stored on the web server, it will affect the website for a longer time. In order to perform stored XSS attack, the malicious scripts should be sent through the vulnerable input form. For example, can be a comment field or a review field. This way, the appropriate script will be saved in the database and evaluated on the page load or appropriate function calling. In a stored XSS example, the script might have been submitted via an input field to the web server, which did not perform a sufficient validation and stores the script permanently in the database. The consequence of this might be that this script is now being delivered to all users visiting the web application, and for example, able to gain access to the user session cookies. In this attack, the script is permanently stored in the web app. The users visiting the app after the information retrieve the script. The malicious code then exploits the flaws in the web application, and the script and the attack is visible on the server side or to the app owner as well. The third variant is DOM-based cross-site scripting attacks. This type of attack occurs when the DOM environment is being changed, but the client-side code does not change. When the DOM environment is being modified in the victim's browser, the client-side code executes differently. In order to get a better understanding of how XSS DOM attack is being performed, let us analyze the following example. If there is a website called texting.com, we know default is a parameter. Therefore, in order to perform XSS DOM attack, we should send a script as parameters. A DOM-based XSS attack may be successfully executed even when the server does not embed any malicious code into the web page by using a flaw in the JavaScript executed in the browser. For example, if the client-side JavaScript modifies the DOM tree of the web page, it can be based on an input field or the get parameter without validating the input. This allows the malicious code to be executed. The malicious code that exploits flaws in the browser on the user side, and the script and the attack is not necessarily visible on the server side or to the app owner. By now, it is clear that cross-site scripting attacks are difficult to detect and even tougher to fight against. There are, however, plenty of ways one can safeguard against such attacks. Let's go through some of these preventive measures. Like mentioned earlier, XSS attacks are sometimes difficult to detect. However, this can be changed if you get some external help. A way to prevent XSS attacks is using automated testing tools like Crash Test Security Suite or Akinetic Security Suite. Still, manual testing is highly time consuming and costly, and therefore not possible to be done for every iteration of your web application. Consequently, your code shouldn't be untested before any release. Using automated security, you can scan your web application for cross-site scripting and other critical vulnerabilities before every release. This way, you can ensure that your web application's live version is still secure whenever you alter or add a feature. Input fields are the most common point of entry for XSS attack scripts. Therefore, you should always screen and validate any information input into data fields. This is particularly important if the data will be included as HTML output. This can be used to protect against reflected XSS attacks. Validation should occur on both the client side and server side as an added precaution. This helps validating the data before it's being sent to the servers and can also protect against persistent XSS scripts. This can be accomplished using JavaScript. XSS attacks only appear if any user input is being displayed on the web page. Therefore, try to avoid displaying any untrusted user input if possible. If you need to display user data, restrict the places where the user input might appear. Any input displayed inside a JavaScript tag or a URL shown on the site is much more likely to be exploited than the input that appears inside a division or a span element inside the HTML body. Protecting against XSS vulnerabilities typically requires properly escaping user-provided data that is placed on the page. Rather than trying to determine if the data is user-provided and could be compromised, we should always play it safe and escape data whether it is user-provided or not. Unfortunately, because there are many different rules for escaping, you still must choose the proper type of escaping before settling on a final code. Encoding should be applied directly before user controllable data is written to a page because the context you're writing into determines what kind of encoding you need to use. For example, values inside a JavaScript string require a different type of escaping to those in an HTML context. Sometimes you'll need to apply multiple layers of encoding in the correct order. For example, to safely embed user input inside an event handler, you need to deal with both JavaScript context and the HTML context. So you need to first Unicode escape the input and then HTML encode it. Content Security Policy, or CSP, is a computer security standard introduced to prevent cross-site scripting, clickjacking, and other code injection attacks resulting from the execution of malicious content in the trusted web page context. It is a candidate recommendations of the W3C working group on web application security. It's widely supported by modern web browsers and provides a standard method for website owners to declare approved origins of content that browsers should be allowed to load on their website. HTTP only is an additional flag included in a set cookie HTTP response header. Using the HTTP only flag when generating a cookie helps mitigate the risk of client-side script accessing the protected cookie, that is if the browser supports it. If the HTTP only flag is included in the HTTP response header, the cookie cannot be accessed through a client-side script. Again, this is if the browser supports this flag. As a result, even if a cross-site scripting flaw exists and a user accidentally accesses a link that exploits this flaw, the browser will not reveal the cookie to a third party. If a browser does not support HTTP only and a website attempts to set an HTTP only cookie, the HTTP only flag will be ignored by the browser, thus creating a traditional script accessible cookie. As a result, the cookie becomes vulnerable to theft of modification by any malicious script. Next on our docket is a live demonstration where we solve a set of cross-site scripting problems starting from the basic level to the topmost level 6. We're going to start at level 1. In this web application, it demonstrates the common cause of cross-site scripting where user input is directly included in the page without proper escaping. If we interact with a vulnerable application window here and find a way to make it execute JavaScript of our choosing, we can take actions inside the vulnerable window or directly edit its URL bar. This task needs only basic knowledge. Let's see why the most primitive injections work here right away. Let's do a simple query and inspect the resulting HTML page. I'm going to use this phrase with a single quote as a special character. We can now inspect the HTML page. We can see here in this line, the special character single quote appears in the result over here. The provided query text is placed directly in a B tag, as in a body element. We need to perform a reflected XSS into the web application because they are non-persistent XSS attacks and the payload should be included in the URL to perform successful exploitation. We can use any payload, but we're going to use the simple one to perform an alert in this web application. It's simple and can be shown easily. We're just going to write the script over here. And we're going to press search. As you can see, we have successfully launched our first cross-site scripting attack. We can see an alert box pop up with the necessary message, and a similar process can be used to steal browser cookies and passwords, albeit with different commands. Now we have the option to move to level 2. In this web application, it shows that how easily XSS bugs can be introduced in complex chat applications. Chat app conversations are stored in a database and retrieved when a user wants to see the conversation. Therefore, if a malicious user injects some JavaScript code, all visitors will be infected. This kind of cross-site scripting attack is more powerful and it is more riskier than reflected cross-site scripting attacks, and that's why it is known as stored XSS. I posted my query with a special character of a single quote, and this is what I get. Whatever I typed in simply appeared on the page right after I click on Share Status. Let's see the source. You can see here, the text I posted seems directly put inside a block code tag. So even a simple script tag we used in level 1 should work here, but it will not. Let us examine the code to understand why. We're going to toggle the code over here and check the index.html file. Important part is line 32. The generated HTML fragment, which is the HTML variable in the code, is added to the mail HTML using the inner HTML method. So when the browser parsing this HTML fragment, it will not execute any script tag defined within that HTML fragment. HTML parser will not execute a script tag when it parses HTMLs via this method. This is why the script tag like we used in level 1 is not going to work here. Our solution is to use events. Events will execute the defined JavaScripts. We're going to use an image over here. And when we press on share status, in the above injection, we are loading an image that doesn't exist, which causes to trigger an onError event. In onError event, it will execute our alert method. With that, we are able to beat level 2, and we can now move up to the next level in our challenge. As you can see, clicking on any tab causes the tab number to be displayed in the URL fragment. This hints that the value after the hashtag controls the behavior of the page. That is, it is an input variable. To confirm, let's analyze the code. As you can see in line 43, inside the event handling, the value provided after the hash in the URL is directly passed onto the choTab method. No input validation is being performed. The value passed to the choseTab method is directly injected into the img tag in line 17. This is an unsafe assignment and it is the vulnerable part of the code. Now all we have to do now is to craft a payload that would adjust the img tag to execute our JavaScript. Remember, the script tag from level 1 would not work here since the variable HTML is used to add the DOM dynamically. Hence the events are our aces here once again. I will choose to use the existing img tag and change the source to something that doesn't exist, hence forcing it to fall in to execute an onError, even which I will pass the URL. Once we visit that URL, we can see that our Java pop-up has opened up here with the same message of XSS level 3 has been completed. With this, we can now move on to level 4, which is going to present a different kind of attack. In this web application, there is a timer on the page. That means whatever numbers we put in the box, a countdown starts. And then when it finishes, the application alerts that the countdown is finished. And we can see the time is up pop-up appearing over here, and this resets the timer again. Now it is obvious that the value entered in the text box is transferred to the server over the timer parameter in the URL. Let us examine the code to see how the timer parameter is being handled. We're going to visit timer.html over here, and we're going to check over here. In line 21, the start timer method is being called in the onload event. However, the timer parameter is being directly passed to the start timer method. We need to perform a pop-up alert in the web application which escapes the content of the function start timer without breaking the JavaScript code. The parameter value is directly added to the start timer method without any filtering. What we can try to do here is to inject an alert function to be executed inside the onload event along with the start timer method. We're going to remove this argument and put our script over here. Now when we press on create timer, and we have a pop-up with the XSS level 4 completed. We can now move on to level 5. In this web application, this application XSS is different because this challenge description says cross-site scripting isn't just about correctly escaping data. Sometimes attackers can do bad things even without injecting new elements into the DOM. It's kind of open redirect because the attack payload is executed as a result of modifying the DOM environment in the victim's browser. This environment is used by the original client-side script so that the client-side code runs in an unexpected manner. The vulnerability can be easily detected if the next link in the sign-up page is inspected. The href attribute value of next link is confirmed, which is exactly the value of the next URL query parameter, as you can see over here. This means using the next query parameter can be used to inject a JavaScript code to the href attribute of the next link. The following is the best way to do it. As soon as the user clicks on the link, the script will be triggered. We're going to press anything random. And now that we click next, we can see the XSS level 5 that we had provided in the URL as a parameter to the next variable. Since the value of next provided appears on a pop-up, we can consider the attack a success and move on to the final level 6. In this web application, it shows some of the external JavaScript is retrieved. If you analyze the URL, you can see that the script is loaded already. The vulnerability lies within how the code handles the value after the hashtag. If you check on line 45, the value right after the hashtag is taken as the gadget name, and then in line 48, the value is directly passed on to the include gadget method. And in the include gadget method that we can see over here, you can see in line 18, a script tag is created and the URL gadget name parameter value is directly used as the source attribute of the script tag in line 28. This means we can completely control the source attribute of the script tag that is being created. That is, with this vulnerability, we can inject our own JavaScript file into the code. We can inject a URL of our own hosted JavaScript into the web application's URL after the hashtag, and the URL should not be using HTTPS but anything like that to bypass the regular expression for security checking. We're going to remove the pre-stored URL and we're going to load our own JavaScript file. Finally, we have reached the end of our challenge. We completed 6 different varieties of cross-scripting attacks and used different solutions for all of the 6 questions. Hope you learned something new today. If you have any questions regarding the topic, feel free to ask us in the comments below and we will get back to you as soon as possible. Subscribe to our channel for more informative videos and thank you for watching.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.